Hello, everyone. My name is Karan Matnani, and today I'll be presenting our paper, What's Mine is Yours, What's Yours is Mine, Simplifying Significance Testing with Big Data. Introducing my colleagues. Valerie Leptak is an applied scientist at Amazon. George Foreman is a principal applied scientist in the same group. About myself, I work closely with George and Valerie. I've been at Amazon for the last 6 years, and I work as a software development engineer who wears both hats, that of an engineer and of a scientist. I got my bachelor's degree in engineering from Pune University in India in information technology, and my master's in computer science with a focus on machine learning and natural language processing from Columbia University in New York. I joined Amazon in 2015, and since then I've worked in the domains of search, ads, personalization, and now geospatial, currently with Amazon Last Mile Tech. So let's see what Last Mile is. I'm going to play a video for you. So Last Mile is a delivery arm of Amazon. At Last Mile, we deliver in countries worldwide. We take packages from the delivery station all the way to the customer's house. To do this, drivers use an app through which we communicate with them. And in that app, they see points where they can park the car on the map, and they see points where they want to drop off the package. This point, where the package is dropped off, is called the delivery point. The little infographic on the right shows you the 2 points the driver has looked at, one to park the vehicle and the second to drop off the van. My group focuses on generating these points. Now, as you can imagine, these are all complex processes that require experimentation. Every small change that is rolled out to customers can affect millions of customers. So at Amazon, we like to follow the gold standard of experimentation, which is controlled experiments. In a controlled experiment, there's a control group and a treatment group. Your whole data set is split into these two parts. And your experiment is basically applied to your treatment group, where you hope to see the effects of your experiment. So an important decision to make there is how will you split your data fairly so that the outcome is something you can believe. In doing this, there are three things we worry about. Number one is selection bias. So selection bias means that you've managed to pick two groups wherein there's already an inherent difference between them before the treatment was applied. That's not what you want. So imagine an experiment running in Europe, and imagine that UK is in the control group and Spain is in the treatment group. Now, if it's winter and it's snowing, the roads are icy, the drivers are going to walk slower and drive slower in UK and not so much in Spain. So there's already a selection bias in the group selection. So that tells us that you cannot select something so largely different from each other that the experiment doesn't mean much. So you go into a higher granularity, which means you go lower down. Now, at Amazon, we can divide it right up to the point where you deliver to the particular house. And so every house can be in control and treatment. But what happens if you go into such a high granularity? That's the other problem, mixing. Mixing means the effects of control and treatment have leaked into each other, thereby diluting the effects of the experiment. So imagine that you've got two packages coming for two neighbors, one for you and one for your neighbor. And Amazon has a van that's sent to your place for that. The delivery driver may park the van right outside your house and then walk up to your place, drop your package. Then taking the neighbor's package, which he already carried along from the van, along with him in the van, goes off to the neighbor's house and drops it over there. Walks back to the van. Now, in doing this, because you and your neighbor were in control and treatment groups, the driver doesn't know that. The driver has inadvertently introduced mixing by mixing the effects. So these are two things that can make experiments be not meaningful. Power is an important dimension. This tells us that there's an ability to detect small effects of the applied treatment. Every second of improvement matters at a certain scale. So you don't want to leave anything on the table, and so high power is useful. And so the choice that you have here is that of picking the right key. This is the randomization strategy. How will you randomize your data such that certain keys fall in control and those in certain and all the others fall in treatment? And in the real world now, there are four realistic choices we have in the geospatial world, that is. So to divide something by delivery station, which is multiple postal codes grouped together, to divide something by postal codes and street name and building number in the increasing order of granularity. So let's look at an example. This is the island of Manhattan divided by postal codes. Red is control and blue is treatment. Let me annotate something for you here. So if you look at this blue patch here, this is Central Park. Now, because it's a central park, obviously we don't have too many deliveries in this large blue patch. And the areas next to it, this red one and this red one and this blue one, all will have much higher density of deliveries because there are a lot more people living over there. So there is some selection bias here, depending on where this big blue patch goes, whether it goes to control or to treatment. That's a selection bias problem. So then delivery station will have that even more, right? They will have multiple zip codes together. So depending where it's split by, we'll have more selection bias. So then we can examine the other two, street name and building number. Let's look at those. So on screen, we've got on the left, you've got the thing divided by street names. Now with street names, an important thing to notice here is that all these dots, first of all, are delivery events, the red ones and the blue ones. The red ones are in control and the blue ones are in treatment. So this whole street, for example, is divided such that this is all in treatment and this street is all in control. An important thing to notice is these intersections. This is where mixing happens. So in a division by street, we'll have all this mixing only at intersections where there is a control and treatment street. With building numbers, the mixing problem is even more. So now you can see there's no selection bias. There's almost no selection bias here, right? We've gone really deep. And so in these places, everywhere there's an overlap like this, where you see the red and blue overlapping, there is some mixing that's bound to happen. So I'm going to discuss these key problems. Let's think about how we can detect them and how to pick the right level of granularity that minimizes both these concerns. Our main focus is on significance testing. Significance testing tells us that the difference between control and treatment is not by chance, but due to our intervention. Traditionally, we've used the t-test, which is really popular. In this, we determine ahead of time what our control and treatment splits were. And there should be no difference because we haven't applied any treatment before the experiment. The t-test itself is a parametric statistical test that determines whether two samples were drawn from the same underlying distributions. In our case, pre-experiment, we want that to be the case. We want no inherent difference between these two. Right? Now, P is the probability that they came from the same distribution. So we ran 1,000 simulations in AA mode, that is pre-experiment. And we expected that at P equal to 0.01, less than equal to 0.01, the number of significant runs would be about 1%. And that's what would be a realistic expectation, given that we're in pre-experiment mode. But this is what we saw instead. On the screen, you see that the number of significant runs is way higher than expected. Let's take a look at postal codes, for example. 97.8% of the time significance was declared, whereas it was supposed to be 1%. So then we pivoted to the permutation test. An important thing to mention is that the reason the t-test had all these issues was because we violated some assumptions, those of normality of data and independence of data. The permutation test is low on assumptions. It is more expensive, but it is low on assumptions. So that's what we pivoted to. Now, in a permutation test, you resample the data repeatedly to get a set of permutations. In our case, since this was first tested before the experiment, we wanted to see that there was no inherent difference between the control and treatment splits. Right? The permutation test, by definition, gives us 1% significant runs. And that's what we want. So once we'd established the choice of what test to use for significance, which is the permutation test, we applied it to all of our data in AA mode. One big question we had was that how do we know we're able to appropriately detect a business significance difference? So use confidence intervals for that. And as you can see, the confidence interval starts narrowing as we go lower down. The mixing that you saw on the previous slides shows us that this is in line with our intuition, that the amount of mixing increases as we go lower down, which is bad. So hence this arrow is red. And the confidence interval getting narrower makes it more sensitive. So that's good. So this arrow is blue. Now, seeing that we are in AA mode, there's obviously not going to be much difference if you've done it right. And so we can't directly use confidence interval exactly in the AA mode. So we designed a power test wherein we apply a simulated minimum business significant difference, in this case, 1 second of difference, and see if we're able to detect it, despite this mixing and despite the selection bias. And here are the results we saw for the simulation. So this is the same mixing you saw on the previous slide. increasing this order, confidence intervals narrowing down in this order, and the applied difference, the false applied difference in treatment, where we said that we assume we ran an experiment that improved our metric by 1 second. So this is approximately a second. It's not exactly a second because of the number of groups and some mixing. In this, we noticed that improvement was not detected in the delivery station or in the postal code. So if we can't detect a 1 second improvement, which is significant to our business, then we can't use these choices. So these were out. Between these two, they both did detect significance. So we could pick either or, but the mixing was far higher in buildings. So we went with street. So street became our choice going forward for experiments that had such metrics we cared about. We applied it to an experiment in the real world. And here we saw that significance was declared in 2 out of these 3 metrics. In the continuous number metric, significance was declared, and it's in red because there was a regression. In metric number 2, significance was declared and it was green, it was the right direction. Third one had no significance. Now, this led to more deep dives later on, and we focused on this part to figure out what was wrong, and this part was assuring that we were in the right direction. But the point is that the permutation test helped us make this decision confidently because we know exactly what happened because of it. Now the permutation test has wide applications, especially in non-normal distributions. On the right, you see a heavy tail distribution. This is what we really observed, and so this is why the t-test didn't work for us, because it violates the principle of violates the normal data assumption. And here it's non-normal distribution. Another good application is an outlier with an outsized impact. Imagine a sales company where 40% of the revenue comes from one client. In such a case, the permutation test can help. So in conclusion, permutation tests used to be very difficult to run because they were computationally intensive, but now we've got the computation power to try them out. We showed that they are applicable in a variety of metrics that we used, and they help you make a choice of what granularity to split by in the randomization strategy. We provide a decision framework that helps us do that and can help you do. Thank you for listening. What questions do you have?